All right. So now let's route this guy. In the schematic, I told you guys there was a wire tool, and in the board there is a wire tool as well, but you have to be careful because, well, here by default the wire was on top, but it might have been on some other layer, but you might not be able to do anything meaningful or what you intended. So by default it was on the top layer, and you'll notice here layer 16 is the bottom layer, so we have 2 layers to wire on, but you shouldn't depend on that. The tool you're going to want to use instead, just like we did, is not net but route. If we type in net here, it'll give us an error. The net command can only be used in a schematic. So for the board, they give us a special command called route, and so if we type in route, we'll be given all these interesting settings, and you'll notice that the layer, it only tells us there's 2. Eagle supports up to 16, but since we're using the Autodesk DRU, it'll give us only the options that are available for the 2-layer design, which is top and bottom, layer 1 and layer 16 respectively. So with our route, we'll have all these settings. By default, it walks around obstacles, and what that looks like is it walks around obstacles, so we can't actually wire things through the pads. We can't wire things through other bottom layer pads. We can't wire things through holes. We can't wire things outside the board. However, we can wire things under pads that are on the top layer, so that's why we can go through it. So just to give you an idea, it's kind of makes it dummy proof in terms of accidentally wiring something silly. You can go ahead and turn it off if you want, but I wouldn't recommend it. There's some other options that you might want to explore. It can help push wires around other wires if you're routing them. There are wire bend styles, just like there were in the schematic. Here, I would recommend using wire bend style 1, which pretty much means 45-degree angles, and it has to do for a couple of reasons. The first is manufacturing. When the manufacturer manufactures your board, it actually prefers to have 45-degree angles and not abrupt right angle turns. That's just what I've read up on. The exact reason I'm not 100% sure, but I heard 45-degree angles are better for the CNC machine or whatever machine they're using. Also, in terms of actual electrical behavior, so this is not a high frequency circuit, but if it were, wires at 45-degree angles or even these meandering wires are better for reflections at high frequencies. So you're going to notice that the width is set to 0.1524 millimeters, which is extremely intuitive, right? It is not. So one of the things that by default or the convention is people use mils when they talk about their wire width. So that is 6 mils. So if we do route 6 mil, notice how the width doesn't change. If we do route 10 mils, it'll change to 0.254 millimeters, which is 0.1 inch. When we do vias, it'll do round by default. We're more than welcome to change them. I personally like round, and the diameter of the via is auto, so it'll be automatically determined, and the drill size, so this is the actual hole size or the ring. Right here would be the drill, and the diameter would be the outside ring, and that is determined by auto. You're more than welcome to set it. Autodesk does have a limit. I think it's 14 millimeter for the diameter, and their minimum drill length is 10. So we're going to go ahead and use 10, but remember, this is 10 mils. That's how they specify it. So if we type in 10 mil here, it'll automatically do the unit conversion for us, which happens to be 0.1 inch drill size. All right, so one thing that I will point out now, it's kind of weird how we're in millimeters here, as we can see here, but we still want to route using mils, so maybe we should be using mils. I think that is the industry standard. However, it's more intuitive for me to use millimeters, so I'm going to use millimeters for placing the board components, but actually for wiring, I will be using mils. All right, so we're going to route 6 mil. That's fine for this, and let's start making some of these connections. So if we want to line this guy up real quick, we can move it. If we can't get it perfectly aligned, as you'll see, what we can do is we can change the grid spacing. Earlier, we set the alt to be half, so how do we use that? What we do is on your keyboard, when you move, you're just moving from snap to snap. However, if you hold down alt, you'll notice that it snaps at half, and that's because in our grid, we set the alt to be 0.5. If we change it to 0.1, when we move and hold down alt, it'll change it by a 0.1 snapping area. So that's what we'll use to get it pretty darn close to perfect. See, it's perfectly straight here. We'll do it for this guy too. And you're going to notice these red outlines here. These red outlines are for you to design without getting things too close together. It'll be flagged by the DRC if they're inside each other. And the reason is because when you print your board, if you put something too close like this, see how the DRC is not yelling at us about the pads? Put it a little bit closer. Now the DRC is saying this is way too close. Our manufacturing machines may not guarantee your design to be working in that way. And also if it was this close, which is manufacturable, the silk screen will be running over each other. However, this would be really hard to solder. These points are less than half a millimeter away. This is probably like 0.1 millimeter or so. And that is close solder. So what we have done is in all our libraries, we put this T keep out layer, which pretty much says anything on the top side should keep out of this. And that's to protect you from putting things too close to be able to solder it or for the manufacturing capabilities. So I would recommend, you're more than welcome to break the rules and put them inside, and you'll probably be okay when you manufacture it, as long as you don't come too close for the DRC to yell at you for the pads, because this is what's set up by Autodesk. The red here, the red outline is what's set up by us. So let's go ahead and line these up. You don't have to do this if you don't want to, but when I design boards, one thing that I feel that's great about being an electrical engineer is designing PCBs is the closest thing that I get to art. Of course, there's other things that we can do, but this is what I consider my art. Cool. So I'm going to move some of these closer together. This one doesn't have an outline. It should, and maybe when you guys follow me, it'll have the outline. I should have one there so you guys don't get things too close. This should be fine. Alright, this is how I like it. The switch is on the bottom, so I have to be careful. These are actually probably getting a little close together, but it should probably still be able to slide through. But you have to be very careful to make sure that this battery needs to be inserted through here. I'm going to rotate it. There we go. This is the way it's inserted. It's denoted by this interesting little rivet or so. So the battery inserts through here, and it should be enough to slide through this because this is actually very flat. This is the only part that extrudes outward. All right, zoom to fit. I can make the board a little bit smaller, so I will. We'll move this in a little bit. There we go. So it's still within the design constraint. It would have yelled at us if we made it too close. Cool. So one thing to keep in mind is the larger the board, the more money you're going to pay for it. So it's good to make your designs as small as possible. However, again, since this is an art and maybe some of your designs having things wide or big or some fancy design that makes the board a little bit larger and thus more costly may be what you want to do. All right, so everything is placed the way I want it. Now let's finally route. So again, we'll use the route tool. I want to start with stuff on the top layer, and so I want to make these connections. So you click on the pad and it'll highlight, and notice how the air wire will follow you to where you should route it. So we can go ahead and make those connections. These connections are 6 mil. We can make them thicker. It's probably fine, but this is good for what we need to do. So we'll make the connections. For the power connections, I want to make them thicker, and that's because they're going to be carrying current. They're not going to be carrying a lot of current. We can probably get away with 6 mil for everything on this board, but I want to show you guys some good design practice, and that is the power connections should be made larger. It depends on your design or how much current they're going to be carrying through, but here it doesn't matter. So let's go ahead and route 10 mil for VCC. Notice how I clicked on it. Even though I was routing on the top before, it automatically changes the bottom because I clicked on a bottom pad. If I clicked on the top here, it would be red. If I clicked on a pad, a through-hole pad, then it would be whatever we had last set here. So in this case, the top. So I'll make a top connection here, and it makes sense for me to make a bottom connection here, except I'm going to hold off on that and make a bottom connection that goes about this far. And then what I'm actually want to do is I'm going to switch to the top layer. The reason for that is because I'm going to make a ground plane for the bottom connections, and I want those to be as small as possible. So to do that, you click to start your route. If you're using a mouse, you can do a middle click. Unfortunately, if you're using a trackpad, there is no middle click. So you have to go here to the layer selection and change it to the top. So while you're routing, you change it to top, and you're going to notice that a little via appears here. And a via is pretty much like a little portal or a way of connecting the top of the board to the bottom of the board, or from the bottom of the board to the top of the board. So once you click, you'll notice that it changes to a top wire, and we can finish our connections here. And now we need to make this connection. So this one's going to start on the bottom, and we'll make all of the connections here on the bottom for this guy. I'm actually going to go not the shortest route here because I don't want to disrupt this ground plane that we're going to have very soon. And I'll make my connection here. We can move the wire if we want to make it a little bit smaller. And for this other connection, so this is connecting the positive side of the battery connector. And notice how that air wire that was here disappeared because now we have a full loop. If we do show N$5, which is the name of that wire, it'll show us our connection. So now we have ground, and we could go ahead and route those, except I'm going to show you guys a little more powerful and advanced concept, which is what you should employ in all your designs, is what's called a power plane, or in this case, a ground plane. So to make a ground plane, we type in polygon, we choose the layer we want to do. We're actually going to do one on both sides. In this case, the bottom layer is all that matters, but in most of your designs, you may want to put it on both layers. So I'm going to do bottom, and then we're going to draw, it could be outside of our board. I want to draw it on our board, and I want to make the width 6 mils. Enter polygon, draw on the outline of the board, or further out. Again, that's fine. So one thing that's important is you actually have to connect it for the tool to change. It'll ask you to name it. We want to name it ground, GND. And so now if we type in rat's nest, I told you guys earlier that when we do this with a ground plane, it'll make the polygon connections. So if you look at all the grounds, you're going to notice that the ground here is connected via this. The reason why it's not continuous here is because it has something called the thermal, and the thermal makes it so that it's easier to solder. Because when we actually go to solder this with a soldering pan or the reflow oven or the reflow station, you have to heat up the entire ground before this will start to melt solder. So the thermals make it so that it's easier to heat this portion without heating the whole. So for the pad, you'll notice that the ground is connected, and here on the top, you'll notice the ground's not connected yet. So we need to still make those connections. So what I was trying to say earlier is when you type in rat's nest, it'll shorten all the air wires to their shortest connection if we move components, and it'll also fill in the ground pores. If we want to get rid of the ground plane, because sometimes it's annoying to work with, you can type in rip for rip up, and you can do @ symbol, semicolon. I don't know why they chose this. This is just eagle. The @ symbol will rip up all ground planes. And so the ground is ripped up, but notice how the grounds don't show air wires connected to this anymore. So this is because we've already made the connection. Be very careful. If you type in rip up like this and then click on a wire, that's how you delete it. So again, if you type in rat's nest, it'll fill in the ground plane, and you can type rip up or just rip @ semicolon, and it'll rip up the ground plane. All right, so let's go ahead and make another polygon for the top layer. So polygon, select the top layer if you don't have it selected already, and then draw it around here. Make sure they connect. It's going to ask you for the name. Type in ground again. You could make this VCC or some other layer for multiple power planes, and that's totally a viable thing to do in design, but we're not going to do that here because this is just an introduction. So we'll type in ground and nothing happens, but if we type in rat's nest, we'll notice that there's now something on the top, and if you do display minus top, it will get rid of the top layer, and we still see our bottom layer there. So display top, so we can bring back the top layer, and we'll see the connections. And if we look at the grounds here, it's kind of hard to see without the bottom. I'll just get rid of it for a second. See the grounds connected here, the grounds connected here, grounds connected here, and the ground is connected to the pad on the top. So this is how we guarantee that we're connected on both the top and the bottom layer, is through this pad. We could add vias that make explicit connections. That's totally a viable thing to do, and maybe even preferred in some cases, but we don't have to worry about it here. Cool. So pretty much we have a power plane on both the top and the bottom. I'm going to rip them up so it's easier for me to see. And that's it. So we pretty much routed our entire board. So let's make sure that our board is manufacturable by Arcatek. So we'll type in DRC and check. Nothing pops up, and if you look in the bottom left corner, it says DRC, no errors. That means, according to Arcatek, that if we were to send this board out right now, we'll get no errors. So we have to be careful when we say that. If you made an error logically with your board, like this connection is not the right connection, but again, that's something that's meaningful to you, then the board won't work. However, for the capabilities of Arcatek to actually print this board, there are no violations. So just be careful. If you print this board and it doesn't work the way you want, doesn't turn on because you made a dumb or a silly connection, then that's on you. That's not on Arcatek. However, if you were to print this out and you got something that just didn't work, but you passed the DRC, then you may have to take that up with their customer support or so. All right, so we have our ready board. Now we're going to show you guys how to purchase this through Arcatek.